Climate change and decarbonisation is top of the agenda at the moment, especially for the steel industry. There's a whole number of technological options that the industry can choose, and we're talking about lots of those in our recent podcast, Steelcast. One of the options is to take the gases, the waste gases from the steel making process, whether it's the blast furnaces, the steel plant or the coke ovens, and to do something with them, to use the carbon within those gases for a commercial end. Today we've come down to the blast furnace area where there is a pilot project behind us. I'm delighted to be joined by Dr Rhiannon Chalmers Brown from South Wales University, who's going to tell us a bit about this pilot project and what it's trying to do. Rhiannon, thanks very much for welcoming us here this morning. I can see this plant behind us now. It looks quite complex, if I'm honest, but it's here for a reason. Tell us very simply what's going on behind us.
Yeah, so we're taking the blast furnace gas from the blast furnaces and we're bubbling it through the reactor to produce acetic acid as a product.
And that sounds very simple, and I know I've been talking to you, it's much more complex than that, but the blast furnace gas has got a number of components. Can you talk us through what those are? And then that's a bioreactor, isn't it? So what's inside there?
Yeah, so blast furnace gas is composed of carbon monoxide, carbon dioxide, nitrogen and hydrogen. And then inside the bioreactor we've got loads of tiny little bacteria, and they're using this blast furnace gas as their food, and then their waste product is then the acetic acid.
So it's the carbon within the blast furnace gases that is the issue, as we've started to understand, and that's what we're trying to get rid of. And rather than it being necessarily a chemical equation or a chemical reaction in there's a biological reaction, isn't there? And you talk about the bacteria. Explain where those bacteria come from and what that fluid is. And do they literally absorb that gas and then pump out something different?
Yeah, so the bacteria are from sewage sludge. So we go to sewage treatment works and then take a sample, sieve it, and then use it to inoculate the bioreactor. So we're using a mixed culture, so there's all different types of bacteria inside, and they can then use different types of feedstock. So they can use the gases, so the carbon monoxide and the carbon dioxide, as their food. So the same way we would eat our chips, they eat the gas and then they produce acetic acid and volatile fatty acids as a waste product then, which is what we use as our product. What we do then is we build up the concentration of the acetic acid inside the bioreactor, and then we have an in situ extraction system that we've developed ourselves. So we use polytetrafluoroethylene PTFE membrane, and the acetic acid crosses the membrane, and then we get pure acetic acid out the other end.
Yeah, so in basic terms, it's a simple filtration process. I know I'm simplifying it, apologies for that, but it's a basic filtration process, and at the end of it you get acetic acid, or acetate as you described to me earlier. Can you explain to people simply what that is and what it might be used for?
Yeah, so acetic acid is a really useful building block chemical, so we can use that for paints, steel coating products. We can use it to go into other processes to form bioplastics, polymers, all sorts of things. We can use it for animal feeds and lipids, lots of different applications. So it's a really high value product to get out.
Yeah, and as you say, there's some commercial value for that, and that's hugely important. And, we stand here, and this looks pretty small at the moment. Potentially the blast furnaces, which are just behind the camera here, are putting out, several million tons of gases a year. This would need scaling up substantially, wouldn't it? Where do you go next between this and full-scale commercialisation?
Yeah, so there's still quite a bit of work to do on the pilot reactor to collect the data, to understand what we can about the biological reactions and the yields as well. So typically at the moment we're getting quite a lot of carbon utilisation, so up to about 58%, but we think we can increase that quite a bit. So we'd quite like to get up to 98% carbon utilisation.
Fantastic. Listen, it's a fantastic project. It sounds very simple, but it's incredibly complex, and I think it demonstrates the value of the relationships between industry and academia as we're moving towards decarbonisation across society and across industry. And it'll be absolutely fascinating to see how this progresses, how it ends up, and whether it progresses to a sort of commercial outcome. So, Rhiannon, listen, thanks very much for bringing us down here. Thanks for explaining it so simply in what is, I know, extremely a complex process, but very, very grateful to you.
Very welcome. Nice to meet you.